That was nice. How neat was that?
Okay. That's so good.
What am I looking at?
I don't leave. That's my rubber. Okay.
Do you have a sister?
I told you this would happen. I want to fall my face.
Let it be known that the first 5 minutes of this recording is just you guys yelling and carrying on and laughing. And I'm not editing it. I'm very lazy. Kepler identifies 3 laws which effectively predict the motion of what? Planetary bodies. I definitely deleted it because it made me uncomfortable. I'm still unsure whether it's Campbell's girlfriend, or Campbell's sister. Hey, that's a good physics fort. There's a real genuine good physics fort there. Would objects having weird shapes affect the gravitational field? Absolutely they would. It's really hard to predict how they do, which is why we deal with points at a center of mass and we ignore the shape of them.
No.
Strings. We are not discussing string theory today, Alex. Actually, they're significantly more complex than what we deal with, which is points.
It's like 2 less dimensions of the work, right? It's only 1 dimension. The string exists. I think it's fine, right?
Aren't strings like 5-dimensional, 12-dimensional, something ridiculous?
No, it's 11 dimensions of it. In spatial one.
11?
Yeah,
All right, first law. Now, if you're setting up your book to follow along with this, there's obviously going to be first law, a bit of a definition, and then probably a diagram for each, and then a second law, bit of a definition, diagram, third law, bit of a definition, so on and so forth. So leave yourself space throughout and try and keep it all nice and neat and organized. Is it double I? Why do I feel like it's double I? It is double I? Could be better, could be worse. What's that, sorry? There are other things with orbits. Yeah, orbiting bodies always orbit in elliptical paths. Unless they're perfectly circular, which is just a type of ellipse.
None of them are circular.
Oops. Perihelion and aphelion. Why do I have two purples? Dark blue, please. Thank you. F dash. Foci. Foci. Focuses. Fancy version of focuses. Foci. Let's do some annotations. Focus points. Let's annotate some of this. So this is m equals mass. Capital M equals bigger mass. Capital M. Mass in capitals. Focus. This is real focus. This is kind of like an imaginary focus. These are not technical jargon. It's a way of helping you understand these conceptually, okay? Aphelion and perihelion are absolutely appropriate vocabulary, okay? All right, let's break down this messy, kind of confusing, weird-looking diagram. I'll give you guys a minute to catch up on your notes on it, and then we'll talk about it. Yes, yeah. Mm-hmm. I'll propose it to the principal. I'll get back to you. They're already monetized. I think so. Do I have to turn it on? Are there ads? I don't know. Well, I mean, I get like 3 views a video, so probably not making much money regardless. I'll worry about it if I get more. All right, wherever you're at, let's start talking about this. So, a couple of key things here. As Max identified, helium comes from the sun, Helios it used to be called because it was the first discovery of helium, the element. So they thought helium came from the sun, which kind of is not incorrect. Anyway, perihelion means close to the sun, aphelion means away from the sun. There's also another way of talking about which is perigee and apogee. This is for orbiting Earth, G coming from geo, coming from Earth. So that's a different thing. We don't really need to know too much about that. Now, all of this is written with respect to bodies orbiting the sun because back in Kepler's day, he was alive when they only just figured out that bodies orbited the sun. The guy before him, who was actually, I think, Kepler's mentor, what was his name? It's named after him. The Heliocentric Model. Can't remember. Anyway, someone very important who I should definitely know about invented the heliocentric model. So realized that the sun was actually at the center. And I'm going to find out. No, sorry, that's not what I meant. Yeah, no, that's not what I meant. They don't actually say it in here either. I can't remember who it was. Anyway, Kepler's mentor basically discovered the heliocentric model, established that the sun was at the center of the universe and everything was orbiting around the sun. Originally, we believed that everything orbited around the Earth. A lot of people on their phones, I hope it's for physics forts. Nicholas Copernicus, thank you. Yes, Copernicus. Copernicus discovered that we had a heliocentric universe or solar system and established that. And then Kepler came along and went, okay, what does that look like? Now, there's a couple of misconceptions that they used to hold, and a lot of it was related to religion, because obviously back then, even the best scientists in the world were actually highly religious. In fact, you were more likely to be religious as a top scientist because scientists' jobs were to uncover the meanings of the universe, and part of that was diving into religion. So they were very religious people generally. But this was about the time that people started being like, oh, maybe we got a few things wrong about this whole religious stuff. One of them being circular orbits. So one of the first ideas was that the universe was this perfect orbiting system, and it all centered around Earth. The sun was part of it, the moon was part of it, it all came and circled around us in these nice, neat circles. But then they actually had the mathematics available to them to track the motion of stars, planets, and the sun, and they realized it's not consistent. There's something not right about this. The data does not match up. They could not come up with a geometric model, and you've seen those big rotating body models. I think we've got one hidden in there, but I'm attached to a microphone right now. So, they were trying to build these big apparatuses to model what the universe was showing them, and nothing lined up. And it's because they had it wrong. And it turns out who was Kepler's mentor? Copernicus. Turns out what Copernicus and Kepler realized was not only is the Earth not at the middle of the solar system, the sun is, and the planets orbit around that, and the moon is orbiting around us, but it's not orbiting around the sun except for the fact that it's following us around the sun. You know, all these crazy realizations. But also that they weren't perfect circles. That was Kepler's first law. He identified that they're ellipses. Now, if you take, those of you who are doing high levels of math as well, if you take a cone and you cut it on a plane, you get an ellipse. That's what an ellipse is, which is sort of a weird definition, but that's what they are. And they're actually very common in nature, and we see them quite a lot. And one of the situations they come up in is orbits. One of the key things about ellipses, and this really is the major thing you need to take away from this, they have 2 focal points, okay? So if you actually look at how the body is orbiting around it, you can measure it from 2 focus points. If you take the radius from the orbiting body to the major body, and that's going to change constantly as we orbit. But if you take the radius from there to there and a radius from there to there and you add them, it stays constant perfectly the whole time. So as we get closer to this focus point, we get further from that focus point. And that's you won't actually have to do that. It's just an interesting fact. What I do need you guys to take away is the fact that there are 2 focal points, and that's unique to ellipses, and that's actually how our bodies orbit. Okay, and that's going to come up with some facts I'll introduce in the second law and the third But really, that's the main takeaway from this. Terms like aphelion and perihelion, look, we can check your syllabus. I don't know that you'd be asked to actually define that. Let's actually have a quick look here. Recall Kepler's laws, solve problems involving Kepler's third law. Recall that Kepler's third law, yeah, so it's all about Kepler's third law. So some of this will come into understanding Kepler's third law, but that level of detail is not necessary, okay? So key focus is the ellipses and having two foci. Now I call one of them the real focus. Why? Why do you think I chose that one to be the real focus? Right. It's actually the source of our centripetal acceleration in this elliptical orbit, okay? So the sun or whatever is being orbited by the Earth there. So the sun is the major focus there, the real focus, because it's the major mass, all right? Cool. I'll pause and we'll have a look at our physics thoughts. Is this possible? No. It does kind of depend, but probably not. How does an ellipse not have a center? It has two centers. How do you get a prize? Don't ask how to get a prize. I'm going to look up that IP. Cool. I think that's about it. All right, let's move on to Kepler's second law. Anyone need another second? Surely not. Nope. Jenna, are you drawing a beautiful person over there? I can see it from here, by the way. It's good. It looks good. Very creative. Seems irrelevant, but very creative. Second law. Second law. Objects in orbits move faster when closer to the major mass. I'll give you a bunch of alternatives to major mass, but really that's all you need to know. But you could also say to the real focus or closer to the perihelion, because AP stands for away. Away. Perihelion is closer. Sorry? What? What proportional?
Okay, so for the way it is,
Are you asking if they're directly proportional, like distance is proportional to speed?
yeah.
The relationship is not described by a simple equation. Yeah, so yeah, we'll look at it. Give me a second. Let me explain. Objects can move faster when closest to the major mass / real focus / perihelion. As a result, the area covered by All right, this is kind of a confusing statement. It is best explained with the diagram, so Henna, make sure you're getting down your diagram. Oh, not bad. I feel like that's some of my best work yet. No, this thing doesn't have that. It's really just a drawing thing. Good thing I'm great at shapes. You have highlighters or anything like that, or you want to just do a bit of shading, it will probably help with your understanding. So, not currently. Maybe. If I annoy them enough, they might. Not that you guys are on it right now because you're writing your notes down. Aren't you, Kobe? Not that you're on it right now because you're writing your notes down, aren't you? Good. Yes? It doesn't.
It doesn't.
No, I don't think you could use any of these rules except they're not ellipses. More complex than that. Yeah, I don't think there's anything you could take from this. And I wonder as well if that comes down to, I mean, this comes from Newton's universal laws of gravitation. And as we've discussed, gravity does not seem to fit with our other models for quantum scales. Okay, so to make sure this diagram makes sense, let me just explain some of those key points. So where I've said t equals 0, that's when our mass, whatever our mass might be, whether we're talking about the Earth orbiting the sun or whatever, our Earth, the thing that's in orbit, so at this point here, our Earth starts there, and if we count X number of minutes, hours, days, whatever later, we make it to there. Yeah? Now, Kepler's second law tells us that whatever area we cover there, not the distance, not this sort of circumference of this circle or anything, but the area we cover by sweeping our radius across that arc length, that distance, is actually equal to the area we'd cover anywhere else in our orbit given the same amount of time passes. So over on this side, we start counting here, that's our t0, and X number of seconds, minutes, days, whatever later, we've traveled the same area. We can't relate the distances in any way. We can't relate, a displacement in any way. We can exactly relate the areas, and we can then use that to predict positions. Yes? Good question. Very complicatedly, and you are not asked to do it. It is not in your syllabus to ever have to actually calculate one of these areas or compare them or derive the positions of heavenly bodies in an elliptical orbit. Ellipses are hard to do math on. I think you do look at elliptical mathematics in, maybe it's specialist, maybe it's methods, I'm not sure. But it's tricky math and it's not expected for physics. So it's beyond your syllabus. I need you to appreciate that law exists, possibly recognize it in a diagram or make a prediction from some geometric thing given. I do not need you to do any calculations for this, okay? A little bit longer, get your notes down, and then we'll check physics forts, and then we'll go on to Kepler's third law, and then we're done. Done for the year. Party time! Woo, woo. Cool T-Rex though. Is that it? How does... we've already answered that. Did blank option. Cool. All right, can I move on? Can you get it off, Hannah? Yep. All right, third law. This is the big one. This is the meat and potatoes of it. Got it right this time. Said meat and potatoes. What did I say last time?
Meat and beans.
I think I prefer that.
Yeah. Well, I just like meat and beans. Either
Third law.
depends on the.
No, I'm thinking like black beans. Yeah, kidney beans. Yeah. Even baked beans, man. I like it. Okay, the third law. Alrighty. Let's do it like this. T squared is proportional to r cubed. And then let's annotate. Sidereal, that's an R. You're an R. Sidereal period. Sidereal. 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 Sidereal, I think is how it's pronounced. Good. Okay. The R is probably pretty self-explanatory. Mean radius from major mass. Okay, so how far you are away from the sun on average. Again, that's related to, you can add the radius to the two foci, but we actually don't need to worry about that. We can just get an average radius, okay? When we talk about radius of orbits, often that's the R we're talking about. It's an average radius, because of course ellipses, the radius changes. All right, yes?
But when something in a like so cars,
I don't know if there's much evidence of stable orbits in binary planet systems. Okay, I don't know much about it, so sorry. I don't think you would get an elliptical orbit for obvious reasons, unless. Yeah, no, I think it would very much disturb the orbit, so I think it would be totally different mathematics. Now, sidereal period. It sounds really fancy, but it's probably what you think of when I say period. How long it takes to make an orbit. Here's why sidereal is necessary. Can I have everyone's attention in 3? Focus up for me for a second in 2. Just pause with the physics thoughts for a second. 1. When this was originally discovered, if you looked up, you could see a star, and you could know what star it is, or the sun, and you could know what sun it is. And if you then watched, it would, go away and come back, right? It would look like it had made one revolution around you, yeah? So you would call that a period, would you not? Obviously, that is not the period we are talking about here. We are not talking about the 24 hours it takes before we see the sun again because it's a new day, right? Because the sun isn't orbiting us. We need to zoom out and imagine we're fixed against the stars and in the universe. The sun is a fixed point, and we need to imagine the period as being the rotation around that sun, one revolution around that sun. Of course, that's not actually real, right? We would have to pick that frame of reference and fix ourselves in relation to the sun. But really, the sun itself is rotating and revolving around a black hole somewhere, and right? So that's why there's that technical word, sidereal period. It's the period that you would expect it to be when given this sort of diagram. It's one rotation or revolution, through that, okay? Is that okay? Do we want a diagram or a definition of sidereal period? The definitions can get really jargony and technical, and maybe a little diagram. Would that be enough? I can probably give you a good diagram. So sidereal period is if we have our mass, which is also our focus, we get our elliptical orbit. T would be one revolution is the sidereal period. Question, Alex? I don't like the word. I'm guessing it's a reference to the Milky Way and the Andromeda galaxy somehow merging.
Yep.
It makes me uncomfortable. The actual name, but also the concept of them merging. I'm sure that would kill us. Well, that's comforting. All right, with that in mind, let's look at the actual formula here. So the period squared is proportional to the radius cubed. Obviously, that's a pretty complex mathematical relationship to describe. We won't have to do that. What we will do is compare this rule being exactly the same for everything. So remember, when I say t squared is proportional to r cubed, what I mean is t squared is equal to r cubed by some constant, okay? That constant is called Kepler's constant, and it can be ignored because what we can do is we can just divide this side by r cubed, right? And then we're equal to k. And every orbiting body this rule applies for, so k is equal to any other t squared over r cubed. So we can say that the period of a planet divided by the radius on average for that planet is equal to the period for any other planet divided by the radius for that planet. I want you to copy this down. You can ignore that little derivation. We don't care about it. This proved a really, really, really easy mathematical way to predict either the radius or the period of any planet orbiting the sun or any other central mass. So we can actually very easily, if we see a planet orbiting a star, so you can often find stars in the universe, and if you watch a little black spot go in front of them, you know there's a planet. If you can get a powerful enough telescope, you can watch that planet, and after it crosses in front of the sun, you can catch it at its furthest point. You can catch it at its furthest point on the other side. You can calculate an average radius. You can then predict how long it takes to go around the sun so that you can set your telescope up to catch it the next time it comes past. And this is something that they did for a long time to predict the periods of all the other planets and their radius from the sun to an incredible degree of accuracy. Obviously, Kepler's constant had to be constantly refined to get better and better. Thank you. But, yeah, that's something to do. But as it got better and better, so too did our predictions of all of this. Now, if you go to your formula book, you will find this formula. You will find that formula. You will not be given this formula. Because, okay, this formula down the bottom, this, you will not be given that on your formula book, but it is important to remember. But it's not as important because you don't actually need it because you can derive it from that formula. Kind of cool. So if you have Earth and Mars orbiting the sun and you want to compare them, you can actually set them equal because this part here, guess what? Exactly the same for both Earth and Mars. That capital G is a constant, that capital M is the sun. As long as you're talking about two bodies orbiting the same major mass, the same sun or whatever it might be, this is the same for every planet, which means that's the same for every planet. That ratio, that doesn't mean the T is the same or the R is the same, but the ratio is always the same, and it's always equal to this. What's this? There's two possible answers you can give me here. It's Kepler's constant, right? To some extent, except you need to sub in the right mass. But it's Kepler's constant. And it's also Newton's law of universal gravitation. Right? Remember this? The gravitational constant, it does not depend on this little mass. We can just calculate it based off the gravitational constant, the mass of the major object, and the radius. So with these things combined, which literally is what happened, Newton read Kepler's work and said, hey, check this out. And that was incredibly useful as well, because now we can also predict masses of stars. Pretty cool, right? Or if we know the mass of a star, we can predict the period of an orbiting body, or the radius of that orbiting body. So let's do that in an example. Remember, if you have any questions about any of that, Physics Forts is available to you now, live. How's it doing? What is this? Someone made me a thumbnail.
Can we make it to the lesson?
I'll delete it, Campbell, don't worry. This is borderline bullying, guys, this stage. If it wasn't just Campbell. All right. There are actually some good questions here. Are all celestial bodies orbiting something? Sort of depends on your definition of celestial body. It's kind of an older term, celestial body. Obviously, it refers to bodies in the heavens. The sun was considered a celestial body, as was the moon. Obviously, the moon orbits something. The sun technically does orbit something. It's orbiting a black hole at the center of our universe, and that's very likely orbiting a supermassive black hole at the center of our universe, and so on and so forth. And yeah, so probably, yes, most likely. Nothing new? It's coming up to the left, it looks like. Yeah, okay. Padlet updated? Update. Nothing.
Add expansion.
Celestial bodies?
Yeah, so if you just had something which like from another
Mm-hmm.
would
Mm-hmm. Yep, they could still orbit, and they would still orbit in ellipses. It doesn't matter that their masses are the same. Technically, the sun is in a very slight little wobble. Obviously, its wobble is not a nice, neat ellipse because it's been affected by the gravity of multiple celestial objects passing around it. All right, let's do a very simple example using that ratio. Again, that ratio is not going to be given on your formula and data book. It will possibly be asked as a question without being given in the question. It is a ratio you need to appreciate the meaning of, and subsequently you need to know that it's equal no matter what the object you're talking about is. For example, Triton and Nereid are two moons of Jupiter. Triton is 353,000 kilometers from the surface of Neptune. It has a period of 5.87 days. Now, you'll notice the surface of Neptune. Are they really going to annoy us and make us add the radius of Nereid? They are, yeah. Yeah. They give it here. Neptune has a radius of 24,750. So remember, when we're finding that radius for this orbit, the surface, that's from the surface. So the radius of Triton. What? Oh, I see what you're saying. Nereid is, yeah, the center of Nereid. Because Nereid is a small moon, I guess.
Yeah, I know, but it's still weird.
Yeah, it is weird. They've done it just to be hard. So the radius for Triton is equal to 353,000 thousands, because it's kilometers, plus the radius of Neptune, plus the radius of Neptune. So plus Rn. Okay, which is going to be equal to what's that? 24,750,000. So 377.5. Can someone check me there? And the period for Triton is 5.87 Earth days. Now, interesting units here. Remember, and we haven't spoken about this in a while, our formula is going to look like this, right? T squared over R cubed. We're dealing right now with this law from Kepler. Do my units matter?
It's actually 3777.
377.
3 and then 37.
Really? Oopsies. Thank you. And then 4 zeros?
4 zeros.
Yeah, cool. All right, my bad. Remembering what this is equal to. What's this ratio equal to? Huh? Some constant. Some constant was what I was looking for. Yeah, absolutely. 4 pi over gm, blah, 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 right? It's some constant value, okay? Do units matter? What's the units of a constant? Do SI units matter? That's what I'm asking. What are the units of a constant? Constants don't have units. There are no units for constants. They're constant values. They're just a number. They're some ratio. The units, totally irrelevant. Okay. What you do need to know is that if you are setting this equal to the period squared of some other thing r cubed and your units are different across, then your ratio is not going to be the same. That will break things. Generally, I would recommend doing it in SI units regardless at all times, but I don't want to, so let's not. Nereid is 5,560,000 kilometers, so 5,560,000,000 meters. So even though I changed this to meters, we actually don't need to. From the surface of Neptune, so that radius for Nereid, that's the notation I'm using for Neptune, but they use, yeah, so I'm going to use Nereid, lowercase n. This will be a lowercase n. So we can differentiate it from the radius to Neptune, or of Neptune. 5 million, what did I say? 5,560,000 kilometers. I'm going to make it meters by just easily adding on 3 zeros, plus the radius of Neptune, which will give us 24,000. That will become a 5. That will become a 7. That will become a 4. And that will become an 8. Yeah? 0,000 meters. I've changed it to meters. And the period for Neptune, for Nereid, is 359.9 Earth days. And the question asked, determine if these data are consistent with Kepler's third law. What is that actually asking us to do? Right, see if this is correct. Does the period of one planet divided by the radius of that planet equal the period of the other planet divided by the radius of that planet? If that's true, then great, Kepler's law lines up. Let's just do it. TA, so this is going to be T squared divided by RT cubed. Does that equal Tn squared divided by Rn cubed? We just have to sub in our numbers. I'll highlight, you guys actually substitute, okay? So RT is here. That goes in here. Rn is here. No, TT I'll do next. TT is here. That goes in here. N is here. No, they're not, but that's what that conversation before was. Because we're just looking at the ratio between these two things, it doesn't actually matter whether the units are SI. They do have to be the same across the problem, but they do not have to be SI. We could have kept it in kilometers, but it's an easy fix to make there. Wait, I don't want to highlight that. Okay. What do we get? TT is 5.87. We need to square that. We divide that by RT cubed, so divide that by 377750000 to the power of 3. 6.39, what do we get? 6.39 by, hey, let's do sig figs. How many sig figs? 3? Minimum 3? Minimum 3, it looks like. So 6.39 would be correct sig figs. By 10 to the negative 25. Is that equal to the other one? What'd you get? So 7.44 with 3 sig figs. I guess you could technically do Nereid to 4 sig figs, but that's all right. Okay, so that's not correct. Yeah, so the conclusion from this is simply that it is very, very close. Very, very close. And if you actually think about those as actual numbers, that's 0.000000025 times and then some values. So the difference between that, you know, 1 trillionth of a number is pretty marginal. So we're actually okay with that. We're actually okay with that. That's a good question. There is none given in the problem. So you would just discuss, you know, if this was actually an exam problem and they asked you to determine if they're consistent to an error of something, you would actually want to compare them as a actual value. So not exact, but fairly consistent for experimental data. But fairly. Now, to drive that point home, let's have a look at this. If you're still copying that example down, I'll go back to it in a second. Just give me a moment, I want to show you this. This is the law of periods data for selected planets. So you can see there on the right, 2.98, 2.99, 2.96, 2.97, 2.97. So that's an acceptable amount of accuracy, I guess, right? Our problem is not as accurate as that, which is why you could say maybe it's not consistent. There appears to be some difference here, but it's the same order of magnitude at least, and it's fairly close. So it does depend. Okay? Yes. Huh? Video, yes. I think we're done. That's it. Now, I do have the Check Your Learning 5.1, which I'll pop up. And I'll just leave it there. Obviously, when we come back next year, we're going to spend 2 weeks, I think, reviewing chapters 1 through to 6. All of this, all 5. Assuming I'm your teacher, yeah.